Okay, first topic. We have listed on our website a few of the topics that we'll be doing. I have some 10 slides and a live presentation afterwards with some, well, the bits and pieces that I will close up with. But for now, let's start with the first topic. There we go. These are the topics: the current status at SARC, some piping systems, not some piping systems, but the piping systems to be integrated in PIAS, stability over the weakest axis, etc. Well, you can read and probably have read what we see. One of the things that we have recently amended again was our PIAS menu, which has been developing over the years, and we have now icons for every individual module within our software. But I will get back to that later in the live demo. Current status at SARC. Well, not current, but we were established in 1980. That is always a current status, of course. That will never change. We are located in Bussum. The current status is that we will actually be moving, but that's only 300 meters, somewhere within the coming year or so. We have 15 employees. Actually, the photograph on the right, the man on the right-hand downside, Rafael, has left the company, but we have somebody else in his place. Maria is not on there, Bastiaan is not on there, Marion is not on there, so we have more people than in this photograph because they were not all there. And we are a mix of naval architects and programmers. We have one mechanical engineer and a mathematician, which is Maria. Yeah, we spend our days programming and doing project work and providing support and training, etc. All the work you would expect from a software house, plus the engineering and services we provide. There may be something on that in a further webinar later on. Then, the first technical item for this webinar. Damage stability, including piping. For damage stability, there is more and more focus on progressive flooding. I should kill the camera, otherwise I'll be obscuring. No webcam. There we go. You've seen me enough, I think. I hope. Damage stability, including piping. The basic idea is that we would not make logical connections between compartments. So if one compartment is flooded, then the other may or may not also be flooded. But we would replace that by a, well, definition of the actual connection between the two. So not a logical connection. If this tank is damaged, then that tank will be damaged, but a logical connection, actual pipe. And if the pipe is defined with, or the connection is defined between two tanks, then the software will figure out that the connected tanks are maybe simultaneously flooded, or one will follow the other, depending on the properties we define for these pipes or connections. An opening in a bulkhead may also be a connection, or a pipe with zero length, if you like. And by providing attributes for these pipes and connections, we can create calculations in a time domain. If we provide the resistance, or if we define the resistance factor and the diameter of some pipe, or some other resistance of appendages like knees or well, branches, wherever, then we can predict. We know the situation of the vessel, we know what's in the tank, we know the level of the outside water, so we know the pressure differences over the pipes, and basically we can run all calculations in a time domain. And that would be a huge step forward in taking progressive flooding into account. For two reasons. One, it's far more accurate than everything we have ever done and that we know of our competitors. To include this in commercial stability software, I think we're the first. And it would reduce the manual input of what you know of progressive flooding for a specific damage case, because you don't need to define all the logic connections between the tanks if you've defined the pipe already, or the connection as you see on the right hand side. This comes of course with a few menus. You can define a segment or a system consisting of different segments. This is a depiction of, well, some piping leading to two compartments with a branch and a waypoint. So there will be a bend here in the pipe, and well, this is another branch, there will be a Renel vent there, and all the properties of these different features within this system will have well, sufficient meaning and to run the calculations in the time domain. That's very accurate. It may be a bit time consuming, and in many cases it may be overkill. So we've also come up with a simpler system based on the same input and much more comparable to what we do now with the logical connections. That's ratios and delays, and that means that based on this definition, on a connection between two compartments, we can define that the first compartment, let's say the directly damaged compartment, will flood in the ratio of 4, so 4 intermediate stages, and a connected compartment may have a delay of 1 or 2 or 3 steps. So if the first compartment is filled, let's say in steps of 20%, then at 60%, the next compartment with a delay of 2 will only be filled 20% yet. And that would make it possible to scale down a bit from the full time domain calculations into something which is more accurate than what we currently provide, and is a good step for, let's say, probabilistic damage stability, deterministic damage stability, without the restrictions that we had so far. You can define many different connections between two compartments, and compartment A may flood compartment B, and B may flood into compartment C, and C into D, and A may also flood directly into compartment D. And the software will automatically sort out which of the connections would be the first to start flooding compartment D in that case. So a lot of the, well, intelligence that you need to put in at this moment to run realistic progressive flooding calculations will be solved. And also the requirements, let's say, for cross flooding within 8 or 15 or 12 minutes, depending on the requirements, may be solved fairly easily in the time domain calculations without the need to remodel or reconfigure anything. You just switch on the time domain calculations for the things of interest. Okay, I see some questions. What about in definition of ventilation ducts? Yeah, that would be, the ventilation duct can be defined either as a pipe or as a, that's a question actually I'm trying to save a few of them, but a ventilation duct will just be a compartment, and you can connect that to all other compartments as well. So there's nothing special about it. Maybe either defined as pipe, this duct, or as a compartment to be connected to anything else with the proper settings that would be done. Thank you for the question, Zoran, I see. Thank you. Then the next item on my list, and I invite you to share questions with us. I may go into that after the after this webinar, and possibly answer some of them by mail if you leave your mail address to us, or send us a mail directly. You will find us easily enough, because there's very little feedback from you to me at this point in time. Okay, next slide. I only have 10, so don't worry, we'll not be here all day. Healing over the weakest axis. Yeah, typically in shipbuilding, of course, transverse stability was, well, the big issue, of course. Even in the old days, we would even skip trim, so it was really only transverse stability. Nowadays, we have free trim, or yeah, free trimming of a vessel, but that's not the same as calculating your GZ along the weakest axis. For a vessel as wide as long, yeah, stability may be equal in all directions, or for a vessel slightly less symmetric, it can still be that at some specific combination of heel and trim, some opening would be submerged first, and that would be the most critical path in your GZ curve, for instance. Well, we have that as a setting. I will show you later on. And the stability calculations will have a slightly different output, because you will not only have a healing angle and the trim, but you will have a healing angle and the trim angle, and the combined one is the angle set at 30, 40, 50 degrees, etc., depending on user input. The path with the lowest energy, this is basically the path you will find. We could have done this in the polar diagram, but this was the graphic that popped up somewhere, from 0 to 360 degrees. So 0 degrees would, let's say, heel to port side, 180 degrees would be heel to starboard side, 90 degrees is by the bow, and is that correct? No, 90 degrees would be to the bow. And at 360 degrees we are completely round, of course. So it's we could have done this as a polar diagram, then you get like a donut shape, and this may be the lowest path. There is, it's not as easy as this one suggests. It's a lot of work to implement this. That's one. We found a publication that neatly describing it. We have sent that to class for any comment they might have, and we received none, so we just implemented that in accordance with that paper, which is available with comments. So if you like, you can ask for that at SARC on the theory of what we have done here. Currently, we find the path with the lowest gain in energy. That's assumed to be the worst GZ curve. How this should be implemented in relation with the regular stability requirements is something we will figure out as the comments by classification societies will appear, undoubtedly, because I don't think the rules provide for such answers at this moment. We have not found a direct comment on how to check stability along the weakest axis. Possibly some opening may be more critical in one direction and the area in another direction, etc. So what is the GZ, or the direction of the healing for the GZ, which is most critical? It's not clear at the moment, but we'll figure that out when the comments come in. Next slide, the local cloud. That's a fancy name, or fancy, well, it's a name that we thought of for basically complete interoperability of different modules in PIAS. What you see here in a split screen are actually two different PIAS programs. To the left you see layout, and to the right you see fairway. And this is a movie which should start if I press here. Yeah, it does. On the right hand side you see fairway. We're going to play around with that, and we've done this in a movie for, well, the speed of things. And for some other technical reasons we need to update this plan, but it's something we have been developing, and it will be available somewhere in the future. So you see, without any file transfer, this was actually taken in one shot. So with any file output or transfer of data or whatever, one module creates a change in the hydrostatic data of a vessel, and in another module you will see, in this case layout, you will see the tank, well, flip back and forth in, with the modification of the hull form. This is a brief one. It will restart again. So the idea here is that it doesn't restart. No problem. The idea is here that we can open any PIAS module, and that the PIAS model is loaded in the local memory, and bits and pieces of our software are boss of the data in there, and other bits and pieces of our software will read the data from there in the shared memory. So the entire model is loaded, and we can use multiple different modules at the same time. And you can come up with all sorts of practical use for that, checking your compartment volumes while you are working on the hull shape, or checking the intake stability while you are working on the compartments, etc. So there's another example there, actually a three-way split screen, 4 actually. This is something I should introduce. These are the hydrostatic monitors. That means that we have got a monitor for KM with a minimum and a maximum value, and for the volume and for the displacement. So there are some criteria set for these, and this is just a different representation of hydrostatics, of course. If we start this again in fairway, we change a frame, and that frame would of course change hydrostatic. You will see that happening in a moment. There we go. It flips slightly. The values are updated there without any file transfer from one module to another. Then, because of the changed hydrostatics, the resistance prediction by Holtrop and Menne will also have, in this case, a slight variation, which is not realistic, of course, because Holtrop and Menne does not take into account the actual hull shape, but only the derived values from there. And that will also affect the speed and power graph. If I can move slightly back here, thought I could. With the, oh, it just restarts again. I can drag it directly there. So this value will be updated in the speed and power graph. The total power required for a specific speed will go up because of the changed resistance. And so you can imagine all kinds of applications for this local cloud, depending on your design problem. Yeah, open the modules as you see fit. We need to revive this module. It has worked properly, but we have changed so many things, and the storage of all modules in the local cloud is not updated in accordance because we didn't sell it yet. But that will be revived somewhere in the near future, and yeah, just to show what we are doing at the moment. Okay, next slide. Okay, we're halfway our presentation, I think, time-wise anyway. Multithreading, that's another one. Performance of computers has always doubled, laws more in a year and a half. But currently the processors are no longer, do not live up to the Moore's law anymore. But we can, of course, switch on multiple processors if your software is prepared for that. Well, we have done that 3 times actually, because we have multi-threading. We started out with dual threading because the computer came into play with 2 CPUs. So we went along with that, and then we had dual threading. Then 8 cores became fashionable. We did that, and unfortunately that is a different system for multi-threading. We could not just set the number of 2 and raise it to 8 and have octo-threading. That was actually a redesign in another system of, let's say, the administration required for multithreading, because you can, of course, calculate every healing angle for stability at the same time if you've got enough threads available, but you need to merge them again into a single GZ curve afterwards. So there is a lot of work involved in our software to make this happen. And the systems for the administration have changed over the years from dual to octo and now Virginity. I'm told that's 20 in Latin. So we can now run up to 20 cores, and we have high hopes that that will just scale up if more CPUs will be generally available in PCs. 20 cores is now a machine that you can just buy off the shelf, basically. And we can accommodate that. You will not have a speed increase of 20 times, but because of the additional administration, you may expect anything between I don't know, 15 and 18 times as fast as on a single core machine. Yeah, we have some status bars on calculations, and that went, yeah, it didn't go wrong, but it appeared very ugly because they were updated from multiple cores in one go. So a colleague of mine has devised a new screen here on the left-hand lower side, where for each core, this is a probabilistic damage stability calculation. For each core, you can see how long it's working on a single damage case, when it started, which damage case it is, and what it is doing. So if it's ready, if there are no further damage cases to be calculated, it will say ready, and then you will have a better insight in what the computer is actually doing and how long it's spending on a single damage case. So in 8 compartment damage case, I can see that by the 8 point so-and-so, it's 8 compartment damages, number 113. Yeah, that may take a while to run all the calculations and deduct the probabilities for minor damages. Those of you who are familiar with probabilistic damage stability know the frustration on waiting and not knowing for how long, and this will give you a better indication of that. And it will be much faster, of course. That's the whole idea. So that is on multi-threading. Then, look, that was one. No, actually, I had only 9. I was expecting 10, but we had only 9. Some other bits and pieces in a live demo. So yeah, the PowerPoint is done for now. This is our main screen. Well, that was already on the second slide, I believe. One nice feature here, there's an exclamation mark in the news, and that refers to our website. So if I click on that, yeah, it opens on the other monitor, but I will drag it in here. You may have seen this, or you were invited directly through mail. If there is news and I open it, well, you get the latest news. It's a link to the latest news, and now the exclamation mark is gone. So yeah, we try and keep you updated of our news there. Some further things. There are some settings. I want to show where some of them are. The stability calculation method. Perhaps that was a bit quick. Again, in the main menu there is the configuration module and the calculation method and output preferences. The calculation method there is either with fixed trim, that's the old-fashioned way. Trim was remaining 0 to be, well, to make a fair comparison with booklets with hydrostatics for 0 trim and with cross curves for 0 trim, but then free to trim effect, of course. Free to trim effect including the effect of VCG over trim, because the trimming, well, look it up in the manual for the specifics. And then we have the healing around the weakest axis, which is just demonstrated, or not demonstrated, but explained to you. You can just switch between the two and it will just work if you have the module, of course, because we don't share that one for free. Then we have some other things. Previously you would have a few choices. You could run stability calculations to port side, starboard, to the side of heel. So if there was an initial asymmetry in your vessel, either TCG or TCB or both, you'd get an initial angle of heel, and the rest of the software would be to that side. And now we run them both, which is more fair, of course, because yeah, you don't know which one is more critical. Some opening may be lower on the starboard side, but your deck may be higher there, so anything may happen. And the safest way is to just calculate stability both sides. And we do that. I will show you an example in a moment. Then I have a list here next to me, so I should check them on that. For damage stability calculation, typically we use constant displacement. There's an entry on that in the manual for this particular menu. If we say help F1, that's also, well, not new, but some of you may not have seen or realized this, that our help file is now context sensitive. So we open here with on the right page, the writing lever denominator is number 6 in the menu, is also number 6 here. So if we go there, there's some explanation on what we do. That applies to every menu. If it doesn't, we made a mistake, so please inform us. What have we? Now we have the intake displacement minus liquid cargo loss. It says cargo, but basically all liquids in damaged tanks are considered to be spill out. I see some other questions coming in. I will do that after my further presentation. So Denise, if you can bear with us for a moment. This is actually allowed for tankers and for vessels carrying chemicals in bulk, because otherwise you'd have 2 different GZ curves for a situation where the damaged tanks would differ, because the initial displacement may differ, but the end stage of flooding would be identical. It's explained in our manual. I don't want to spend too much time on this, but please look it up and raise questions afterwards if you like. That is what else I wanted to say. And I want to give you some example of things that have changed in HullDef. Our hull definition module, for those of you who may watch but are not familiar with PIAS. Something has changed in the appendages. And what has changed? Well, they are no longer part of the frame. So the frame stops here, but it has a flat deck here. But the hydrostatic model is this, and what you see here on the right and lower side. But the appendages, even if I were to include deck house, I don't know, I haven't studied this in great detail now, 47 up to 49. Let's create a deck house there, not a rectangular slab there, which will be 5 meters wide and 12 meters high. It's too short actually, 51 there. 2 frames are affected. I should of course include double frames, otherwise the discontinuity in the sectional area curve will not be taken into account correctly. But you see, I don't need to add them to the model anymore. They are done automatically as we go along and change bits and pieces here. So you get a direct feedback, and they are added to the buoyancy model, to the hydrostatic model of course, but they are not included in the frames anymore, and that makes life a bit easier to keep things consistent. At least that is our aim and hope for this. Some other feature that is quite useful, has been around for quite a while, but not everybody knows this. Let's say we have a draft mark on frame number 2, then I can just copy this lot, Control C. I can paste it in an Excel sheet, but I can also go to the main dimensions, draft mark, no, not the maximum draft mark, so I always make that mistake. There, a new, which is the draft mark. There, a new segment, reference height minus 0.015, a plate thickness 0.15 with a minus, so the reference is, I keep missing the 0 apparently. Draft mark, open that up, 1 new point and Control V. There I've pasted everything, and I can make this all on the right position, which is 2 meters for frame 4. So there we are. Here we have the draft. I should have copied another set, but this would be the purple line. There would be the new draft mark. I just copied and pasted these coordinates from one place to another, and that may be very helpful in well, any data you want to copy or move or etc. Yeah, we've been at it for almost half an hour, and the idea was to end up somewhere between 20 minutes and half an hour. So what I will do next is look into your questions. Yeah, apparently the first ones are not leading up. This frame is slightly silly, so remove, and now I can do this. I've defined a draft mark. I will check on your questions. One moment. Switch on again, that's me. Denise, would it be any time limit spent for each damage case, in particular damage case with 3 days? When would it stop? No, there is no time limit. The calculation will run as long as required. We may implement a manual break there. For particular, we can spend also a week. Yeah, it's a fair comment. Yeah, that could happen for any particular damage case. You could possibly kill the calculation and switch off that one damage case if such is allowed, or check intermediate results, and I will make it a note if we can basically in the fly switch off one damage case, skip it and move on to the next, so that you can complete the calculation possibly. I will make a note, but I'm not making any promises that we would implement that anytime soon. I see no further questions popping up in the chat window. So for me, that's it. Please feel free to raise any questions, well, in relation to this presentation or otherwise. We'll try our best to answer them all, and we will be back with a further presentation. I cannot give you a real schedule during holiday season, but there will be more. And I hope you enjoyed it, and hope to see you next time. Thank you very much.